The origin of elements, from hydrogen to heavy metals. The origin of elements, from hydrogen to heavy metals. The universe, a vast expanse of space, holds within it an equally immense variety of elements. From the lightest element, hydrogen, to the heaviest ones like uranium, each has a unique story of its own. Origin and journey through time. Exploring the origins of elements unveils the fascinating processes that have shaped our universe, from the formation of stars to the catastrophic explosions of supernova. OB. To understand the origin of elements, we must start with the simplest and most abundant element in the universe, hydrogen. Hydrogen, with its single proton and lone electron, emerged shortly after T. Big Bang, which marks the beginning of our universe. During this event, immense quantities of energy were released, and protons and neutrons started to come together, forming the atomic nuclei we know today. These protons and neutrons combine to create the nuclei of hydrogen, the building block of all matter. As the universe evolved, gravity caused hydrogen atoms to come closer together, leading to the formation of massive clouds known as molecular clouds. These clouds serve as nurseries for the birth of stars. Within these molecular clouds, gravitational collapse and the release of energy initiate the process of stellar formation. The birth of a star commences with the fusion of hydrogen nuclei, Tre, is forming them into helium. The process of fusion occurs when intense temperatures and pressures inside stars cause hydrogen atoms to collide and form helium. This fusion reaction releases immense amounts of energy, sustaining the star's luminosity, providing heat to counterbalance the gravitational forces pulling inward. This delicate equilibrium between fusion and gravitational collapse marks the star's main sequence. Phase. Stars are not eternal, and they evolve over time. When a star exhausts its hydrogen fuel, it enters a new phase. For small stars like our Sun, the next stage is the red giant phase. Here, the core of the star contracts while the outer envelope expands, engulfing nearby planets. During this phase, helium fusion may occur, producing heavier elements like carbon and oxygen. But the story of element creation does not stop there. It takes a cataclysmic event to generate elements beyond helium. This event is known as a supernova. Supernovae are the explosive deaths of mass stars, which release tremendous amounts of energy, outshining entire galaxies. The intense temperatures and pressures resulting from a supernova's explosion provide the ideal environment for a process called nucleosynthesis, or the creation of heavier elements. During a supernova, the enormous energy released fosters the fusion of lighter elements to form heavier ones like silicon, iron, and nickel. This explosive event scatters newly formed elements into surrounding interstellar medium, from which new stars, planets, and even life can emerge. Without the supernova's cataclysmic explosion, the elements essential for our existence, such as oxygen, argon, and iron, would not have been produced. As the universe continued to evolve, galaxies formed, containing vast collections of stars. Within the swirling galaxies, smaller stars with lower masses, like our Sun, continue the cycle of stellar evolution. These smaller stars create new elements through helium fusion during the red giant phase. However, in the grand scheme of the universe's history, this process's contribution to element creation is relatively minor. To explain the presence of the heavier elements in the cosmos, scientists had to look beyond stars. Another significant source of heavy elements is the result of stellar collisions and mergers. When two stars orbit each other closely or even collide, their combined mass undergoes an explosive release of energy that creates yet more complex elements. These mergers can generate elements such as Go, Lb, platinum, and uranium, which have origins in the titanic forces of colliding stars. It is worth noting that the precise mechanisms responsible for the creation of all elements are still not fully understood. New models and theories continue to emerge as scientists strive to uncover the mysteries of element formation. However, with the advancement of technology and the exploration of distant galaxies, our understanding of the origin of elements continues to deepen. Each element found on Earth, within our bodies, and throughout the universe contributes to the intricate tapestry of our existence. From the simplest building block of matter, hydrogen, to the profound ND complexity of heavy metals, every element has a story etched into the cosmos. The study of the origin of elements is a remarkable field that sheds light on the mysteries of the universe. It reveals the intricate processes that have shaped our cosmos and led to the existence of everything we see around us today. On a fundamental level, the origin of elements can be traced back to the Big Bang, the event that gave birth to our universe. In the early moments of the Big Bang, the universe was a hot, dense soup of subatomic particles. As the universe expanded and cooled, protons and neutrons formed, laying the foundation for the creation of atomic nuclei. From the primordial soup of the early universe emerged hydrogen, the simplest and most abundant element. About 74% of all matter in the universe is hydrogen. However, hydrogen alone cannot account for the diversity of elements we observe today. The formation of other elements necessitates the presence of heavier nuclei. The synthesis of elements beyond hydrogen requires the immense pressures and temperatures found within stars. Inside stellar cores, hydrogen atoms collide and fuse together, giving rise to helium-THR. A process known as nuclear fusion. This fusion releases energy in the form of light and heat, which sustains the star and prevents its collapse under gravity's pull. As stars progress through their life cycles, they undergo various stages of fusion and elemental synthesis. In the cores of massive stars, fusion reactions produce elements like carbon, nitrogen, and oxygen. These elements are crucial for the formation of organic molecules and the potential emergence of life. When massive stars exhaust their nuclear fuel, they undergo catastrophic explosions called supernovae. These explosive events release an extraordinary amount of energy, dispersing heavy elements into the surrounding space. It is through supernovae and the subsequent dispersal of their enriched material that elements such as iron, gold, and uranium are produced and distributed throughout the cosmos. In addition to stellar processes, the collisions and mergers of celestial bodies contribute to the creation of elements. When neutron stars collide, for example, the immense energy generated in the impact leads to the formation of even heavier elements, such as platinum and gold. The detection of gravitational waves from neutron star mergers has confirmed this process and highlighted its significance in the origin of elements. The study of the origin of elements is not only a scientific endeavor but also a deeply philosophical one. It raises questions about the nature of our existence and the interconnectedness of the universe. The fact that we are made of stardust, composed of elements forged in the fiery hearts of stars and scattered throughout the cosmos, adds a sense of awe and wonder to our understanding of the world. This story of origin weaves together the elements that make up our world and brings us closer to understanding the grand tapestry of the universe. The process of element creation begins with a momentous event known as the Big Bang. In the hot and dense environment of the early universe, subatomic particles collided and fused together, giving birth to protons and neutrons. These particles would later become the building blocks of atomic nuclei. Hydrogen, the simplest and most abundant element, emerged from this primordial soup of particles. However, the universe's diversity of elements cannot be explained by hydrogen alone. The formation of other elements requires the presence of heavier nuclei, which can only be created through the immense pressures and temperatures found within stars. Inside the cores of stars, hydrogen atoms come together and undergo nuclear fusion, a process that fuses protons to form helium. This fusion releases an incredible amount of energy, sustaining the star's luminosity and preventing its collapse under gravity's pull. As stars progress through their life cycles, they go through various stages of fusion, generating new elements in their cores. Massive stars, in particular, play a vital role in element creation. Their intense temperatures and pressures allow for the fusion of lighter elements to form heavier ones, such as carbon, nitrogen, and oxygen. These elements serve as the building blocks for life itself, as they are crucial for the formation of organic molecules.